Welcome students to the MOOCs course on fuzzy sets, arithmetic and logic. This is lecture number 20. In the last class, we were discussing binary relations between the same set, that is R x comma x. In particular, we discussed three important properties namely reflexivity, symmetricity and transitivity. This has 3 variations, this has 4 variations and transitivity also has 3 variations. Thus, depending upon the nature of the above 3 properties, the characteristic of the relation is defined. In particular, we will look at equivalence relation which is reflexive, symmetric and transitive. For some other relations such as partially ordered set or strictly ordered set, you can proceed in a very similar way and see how those relationships can be defined with respect to crisp sets and also fuzzy sets. Now, reflexivity and symmetricity are easy to verify. From the relation matrix. If it is reflexive, then all diagonal elements will be 1, and if symmetric, the relation matrix R will be symmetric. That is R I comma j, the element at the ith row and jth column will be equal to the R j I, which is the element in the jth row ith column. However, transitivity is somewhat more difficult to establish. The key concept here is transitive closure. A transitive closure of a crisp relation R say x comma x is the relation that contains R x comma x. It is transitive and has the fewest possible elements. That is, given a relation R from x to x, the transitive closure is the smallest set that contains R and also that is transitive. This is achieved by successive composition of R to itself. So, there is a simple algorithm for that one. For achieving transitive closure, step 1, let R prime is equal to R union R composition R. S2, if R prime not equal to R, then R is equal to R prime. That means, the value of R is updated with R prime and go to S1, else return R. The new matrix R will give the transitive closure. To understand the meaning of transitive closure, consider the following graph. There are 4 nodes A, B, C and D. From A we can reach B, from B we can reach C, and from C we can reach D. So, I and J are related if there exists edge from I to J and 0 otherwise. So, in matrix notation, we get the following. R is equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 and finally 0, 0, 0, 0. This is corresponding to A, B, C, D, A, B, C and D. This shows that there is an edge from A to B, there is an edge from B to C and there is an edge from C to D. Now, actually we want if a node J is reachable from another node I, and if we go back to the graph, we see that C is reachable from A via B, D is also reachable from A via B and C, and D is also reachable from B. Therefore, to get the relation reachability, we use transitive closure. So, what we do? R is equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 and 0, 0, 0, 0. So, this we compose with itself. And we use max min composition. So, we get the following matrix. So, minimum of these 4 is 0, minimum of these 4 is also 0, minimum of this here we get 1 and for the remaining we get 0 and for these 4 it is 0. In this way, if we calculate the second row, we get 0, 0, 0 and 1. Check that these 4 are going to be 0 and these 4 rows are also going to be 0. Therefore, R prime is equal to, now we take the union, that means element wise we take the maximum of original R and R composed with R, and therefore, we get 0 1 1 0 0 0 1 1 0 0 0 1 and 0 0 0 0. Since it is different from original R, now we make R is equal to R prime. We now compose this R with itself, where R is equal to the new matrix 0 1 1 0 0 0 1 1 0 0 0 1 and 0 0 0 0, and composing with itself, therefore, we are getting 0 1 1 0 0 0 1 1 0 0 0 1 0 0 0 0, which is giving us, this is all 0, this is all 0, this is 1, and this is minimum of these two is 1. Therefore, when we take maximum, we will get 1. Similarly, this is all 0, this is going to be all 0, this is also going to be all 0, and this is going to be 1. This is all 0, this is all 0, this is all 0, and this is all 0, and 0 0 0 0. Therefore, new R prime after the second iteration is going to be 0 1 1 1. I am taking maximum of these two matrices 0 0 1 1 0 0 0 1 and 0 0 0 0. Since it is different from this R, now this matrix is going to be the new R, and I make a composition with itself. Therefore, 0 1 1 1 0 0 1 1 0 0 0 1 and 0 0 0 0, when we compose with itself, we get 0 1 1 1 this is going to be 0 0 0 1 1. In a similar way, 0 0 0 1 in a similar way. Now, we will get 0, 0, 0 and 0, and finally, of course, 0, 0, 0, 0. Again, if I take the union, new r prime is going to be 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1 by taking union of this with this, and 0, 0, 0, 0. Thus, we get this r prime is same as this r. Therefore, the transitive closure is this matrix, and it shows that B is reachable from A, C is reachable from A, D is reachable from A, C is reachable from B, D is reachable from B, and of course, D is reachable from C. So, that gives the idea of transitive closure. Now, equivalence relation partitions the set into some disjoint classes. Let me give you an example. Let A be any set and X is the power set of A. That means, X consists of all possible subsets of A. Example, let A be the set A comma B comma C. Therefore, X is equal to the set phi singleton A, singleton B, singleton C, A B, A C and B C and A B C. So, these are the 8 possible subsets of A. We define R on X as follows: if x1 comma x2 are contained in X, then x1 is related to x2 if cardinality of x1 is equal to cardinality of x2. Question is it an equivalence relation? So, let us check, is it reflexive? Yes, since cardinality of any x 1 is same as itself. Therefore, x 1 is related to itself. Symmetric? Yes, because if x 1 is related to x 2, then cardinality of x 1 is equal to cardinality of x 2, x 2 is related to x 1, then cardinality of x 2 is equal to cardinality of x 1. Therefore, if x 1 is related to x 2, then x 2 is also related to x 1. Transitivity? Suppose x 1 is related to x 2 and x 2 is related to x 3. Question is x 1 related to x 3? Yes, since cardinality of x 1 is equal to cardinality of x 2 and cardinality of x 2 is equal to cardinality of x 3. Therefore, cardinality of x 1 is equal to cardinality of x 3, which implies that x 1 is related to x 3. Therefore, with respect to the example, we get that phi is not related to any other set, since cardinality of phi is 0. Singleton A is related to singleton B, singleton A is related to singleton C, and therefore, one class is comprising of the three sets A, B and C, because each has cardinality 1. Similarly, A comma B is related to B comma C and B comma C is related to A comma C. Thus, we have these three elements in one class, A comma B, B comma C and C comma A belong to one class characterized by cardinality is equal to 2, and in a similar way the fourth equivalence class consists of single element A comma B comma C, which has 3 elements. Now, to study equivalence relation, on fuzzy sets, or fuzzy equivalence relations we need to extend the concepts of the three properties reflexivity, symmetricity and transitivity for fuzzy relations. Note that a fuzzy relation is represented by a relation matrix R where R I j belongs to the interval 0 to 1 and represents the strength of the relationship between the ith and jth element. That is, R I j is actually membership of the pair x I comma x j to the set R. With that background, let us now define fuzzy reflexivity. If R x comma x is equal to 1 for all x, then R is said to be fuzzy reflexive. If there exists x naught such that R x naught comma x naught is not equal to 1, then R is fuzzy irreflexive. If for all x R x x is not equal to 1, then it is fuzzy anti-reflexive. So, these three are similar to what we defined with respect to crisp relations, but with respect to fuzzy relation, we have another concept, namely epsilon reflexive for epsilon belonging to 0 comma 1 and R is epsilon reflexive if R x comma x is greater than epsilon for all x. So, let me give an example. Consider this matrix 0.7, 1, 0.8, 1, 0.6, 0.5 and 0.8, 0.5 and 1. This is not fuzzy reflexive because these diagonal elements are not 1, but it is fuzzy irreflexive. However, it is not fuzzy anti-reflexive since this 3 by 3 element is or R c comma c is equal to 1. If we change R c comma c equal to 0.4, then it becomes anti-reflexive. But since all diagonal elements of 0.7, 1, 0.8, 1, 0.6, 0.5, 0.8, 0.5, 0.4, all diagonal elements of this matrix are greater than equal to 0.4. This matrix is epsilon reflexive with epsilon is equal to 0.4. A fuzzy relation is said to be symmetric if R x comma y is equal to R y comma x. With respect to crisp relation also we have seen this, but the difference is that R x y need not be equal to 1. That is, if the strength of relationship between x and y is same as the strength of the relationship between y and x, whatever value it is, we call it symmetric. Similarly, if there exists x comma y such that r x comma y is not equal to r y comma x, then r is asymmetric, and if r x comma y greater than 0 and r y comma x greater than 0 implies x is equal to y, then it is antisymmetric. Thus, we find a subtle difference with respect to antisymmetricity between crisp relation and a fuzzy relation. Let me now give examples. For fuzzy symmetricity, consider 0.7, 1, 0.8, 1, 0.8, 0.6, 0.5, 0.5 and 1. This is fuzzy symmetric. If we change this to 0.9, then it becomes fuzzy asymmetric. A relation is fuzzy antisymmetric then both r x y and r y x cannot be greater than 0 if x not equal to y. Therefore, consider this matrix zero, 0.9, 0, 0, 0, 0, 0.6, 0.4, 0, 0, 0, 0.2 and 0.8, 0, 0, 0. This is a fuzzy antisymmetric matrix. Since mu r a comma b is equal to 0.9, but mu r b comma a is equal to 0. Similarly, for other pairs. Please verify that it is fuzzy antisymmetric. A fuzzy relation is said to be transitive if R x comma z is greater than equal to maximum over y minimum of R x y comma R y z. So, this is called max mean transitivity, because in the composition of R x y and R y z, we are using the max mean formula. Mean is actually the standard intersection and max gives standard union. In literature, we may find people have proposed different other composition formula such as max product, that is R x comma z is equal to maximum over y, the product of R x comma y into R y comma z. Then there can be min max, that is R x comma z is equal to minimum over y maximum of R x y comma R y z. So, in different applications, people have tried different way of relation composition, but max mean is the most commonly practiced one. In a similar vein, one can think of using other intersection function, that is T norms or union, that is T conorms. But in this course, we are not going into much details with respect to these different formulae. With that background, let us now explain fuzzy equivalence. Consider the following relation matrix. Suppose we have 7 elements A, B, C, M, N, P, Q, A, B, C, M, N, P, Q, and suppose the matrix is 1, 0.7, 0.3, 0, 0, 0, 0, 0.7, 1, 0.3, 0, 0, 0, 0, 0.3, 0.3, 1, 0, 0, 0, 0, then 0, 0, 0, 1, 1, 0.9, 0.5, 0, 0, 0, 1, 1, 0.9, 0.5, 0, 0, 0, 0.9, 0.9, 1, 0.5 and 0, 0, 0, 0.5, 0.5, 0.5 and 1. So, let us call it R. If we examine the matrix carefully, we see that all the diagonal elements are 1. Therefore, it is reflexive. If you recall the definition that a fuzzy relation is reflexive if R x x is equal to 1 for all x. Also, note that it is symmetric. Now, is it transitive? To check transitivity, we need to compose R with itself, that is R composed with R, and suppose we work on max min transitivity. Let us consider any arbitrary element, say I j, and if we compose, what we shall get. So, let us look at the say second row first column element, the second row is 0.7, 1, 0.3, 0, 0, 0, 0 and the first column is 1, 0.7, 0.3, then 0, 0, 0, 0. What is the max min? 0.7 and 0.1 will give us 0.7. So, we are looking at maximum of minimum of 0.7 and 1, comma 1 and 0.7, minimum of 1 and 0.7, then 0.3 and 0.3, minimum of 0.3 and 0.3, and rest are all zeros. So, I am not going much into the detail, is equal to maximum of 0.7, 0.7 and 0.3 is equal to 0.7. So, this was the 2 1 element of R. In the original matrix, the 2 1 element was 0.7, and after composition also it remains 0.7. I request you to verify for all the 49 elements and see that R composed with R is equal to R. That is, the transitive closure of R, if we apply that algorithm that I have given some time back, after the first iteration itself, we find that R prime is same as R, and therefore, this relation is transitive. Also, if we look at the matrix very carefully, you can see that the first 3 elements are related with each other and the last 4 elements are related with each other. These have been kept 0. Therefore, clear distinction between the elements which are related with each other. Therefore, the question is it a fuzzy equivalence relation? A fuzzy relation is said to be an equivalence relation if for all alpha cuts of the R matrix, the corresponding crisp relations are equivalence relation. Therefore, if we have been given a fuzzy relation matrix, then corresponding to all alpha cuts, we need to verify if we are getting an equivalence relation among the elements of the underlying set. Since it is not possible to check for all possible alphas, what we do? We look at the level set lambda of the relation R. Now, if we look at the matrix very carefully, then we get the different alphas belonging to the level set R 0, 0.3, 0.5, 0.7 and 1. Therefore, we need to check for different alphas and see what happens. We can ignore 0 because 0 cut off R returns the same R. So, let us start with non-zero alphas belonging to the level set lambda. Consider alpha is equal to 0.3, then the matrix that we will get are A, B, C, M, N, P, Q, A, B, C, M, N, P, Q, and we are going to get 1, 1, 1, 1, 1, 1, 1, and here we get 1, 1, 1, 1, 1. And rest are going to be 0. And it is very clear that these are two different equivalence classes. Therefore, we get the two classes to be A comma B comma C and M comma N comma P comma Q. Let us now consider alpha is equal to 0.5. Therefore, the matrix that we get is now that we are taking alpha to be 0.5. So, these elements will become 0 and this will become 1. Here we will get all 1s. So, the matrix now will look like 1 1 0, 1 1 0, 0 0 1, and here we will have all 1s and rest are all zeros. So, that gives us 3 equivalence classes, namely A, B, C and M, N, P, Q. When we take alpha is equal to 0.7, we will have the following. And here we get 1 1 1 0, 1 1 1 0, 1 1 1 0 and 0 0 0 1. Thus, with alpha is equal to 0.7, now we have 4 equivalence classes, namely A, B, C, M, N, P and Q. Extending in a similar way, for alpha is equal to 0.9, we will have A, B, C, M, N, P and Q, that is 5 equivalence classes, and taking alpha is equal to 1, we shall have A, B, C, M, N, P, Q, that is 6 equivalence classes. Thus, what we find that for different alpha cuts, we get the corresponding partitions and each one of them represent equivalence classes. Therefore, we can say that this fuzzy relation is actually a fuzzy equivalence relation. In a similar way, one can look at some other binary relations, namely partial ordering, strict ordering, for partial ordering we have seen or the relation should be reflexive, antisymmetric, and transitive. For strict ordering, that it should be anti-reflexive, antisymmetric, and transitive. We have already extended the definitions of these properties with respect to fuzzy relations. So, one can apply them for a given relation matrix and examine their properties. Okay, students, I stop here today, and with this I complete my chapter on relations. From the next class onwards, I shall start fuzzy logic, which is an important concept with respect to decision making and artificial intelligence. Thank you.